we'll see a small signal approximation of semiconductor diode, which is the most accurate one that we comes across. Now, if you can see that there are two diodes, one is a DC voltage. There is only one diode, and however two signals. One is a VDT, an AC signal, and other is a DC signal, which is passing through the diode. Now, if we consider a small DC signal with AC signal are passing through a diode, and to determine a DC bias point, the diode is modeled by a resistance equal to the inverse of the slope of this tangent passing through the ID line, ID and VD line. A DC voltage a VT and a time varying VDT assumed to have a triangular waveform superimposed on the DC voltage VT. In absence of VDT, the diode will conduct ID given by ID is equals to IDS e to the power VD slash VT. VD is this voltage. Because of it, the diode current will be dependent on the initial voltage. Diode current is equals to saturation current, reverse saturation current into e to the power VD slash VT. Where VDT is applied, then VDT is T plus VDT. That means both the signals are present. Now, we add these signals in the exponential part, in the power part of the exponential signal, and we get this that you can say the time varying diode current. If we add the voltage in the power of the exponential function, then on doing some mathematical calculation, the final result will be ID is equals to e to the power V dt. dt, this is the time varying diode voltage divided by the threshold voltage, and this is the main approximation. I would like to point out at this point that remember that if VDT, that is the time varying voltage, is less than VT, threshold voltage is less than 1, then one must consider this small exponential approximation, that is 1 plus VD over VT into ID. Thus it means that we ignore the time varying exponential function and the VD, that is the DC. This is the DC voltage. This is not, my friends, any time varying voltage. It is the DC voltage. Now VD slash VDT over VT into ID. So this makes the time varying diode current a constant diode current, and it will remain the same throughout. Moving on with the small signal approximation, we can find that VT is equals to 25 millivolts. If you compare it with the last equation, ID is equals to 1 plus VD slash VT, you will find, and then substitute it's just the same. Now the diode conductance will be the differentiation of the ID current with respect to VD current, and you will see that the diode current is equals to over VD voltage. So VD voltage. If we consider it over differentiative over VD voltage, then it comes out to be ID over VT. And the inverse of the small signal conductance of diode, small signal resistance, will be reverse of the conductance, which is VT over ID. Look at this small table. For DC, RD will be equals to VT over ID, defined as a point on the characteristics. For AC or dynamic, RD is equals to VT over ID. VT is the threshold voltage, 26 millivolt over ID, defined by the tangent light at the Q point. So it is not dependent on the AC voltage. Moreover, it is dependent on the threshold, constant threshold voltage. divided by the ID. Now, for our average, we'll get the difference in VT over difference in ID. It forms almost a straight line. So the approximation will be like a slope. Moving to the